Hello everyone, my name is Junaid. I welcome you all to today's class. In this class, we will be discussing about force exerted by the jet on a stationary vertical plate. The schematic looks something like this. We have a pipe and a nozzle is fitted to the pipe and the jet of water is coming out with initial velocity capital V, and on the path of this jet we have a vertical plate which is stationary, right? So now in this class we will be discussing about the force that is exerted by the jet on this stationary vertical plate. So how we are going to be discussing about the force, right? We know that force is equal to F, summation of F is equal to ma. So this is Newton's second law of motion, or you can say that this is the impulse momentum equation. The force exerted by the jet on a stationary vertical plate, or also if we want to find the opposite force that is applied, that is exerted on the jet of the water by the plate using the Newton's third law, right? So let us go and see that. Let us modify this equation m dv dt. Then we can write m over dt into dv. dv is the initial velocity minus final velocity in this case, and m over dt is the mass flow rate here. So see, we have the velocity, so it means that we need the velocity, initial velocity and the final velocity in the direction of x. If we want to find it in the x direction, we need it in the x direction only, right? So what is the initial velocity in the x direction, or you can say in the direction of the jet of the water? So this is the direction of the jet of the water, or I can assign it x direction, and the perpendicular direction to this is going to be our y direction, right? So in the x direction, it's very important to note here that here you can see at this point, there is no velocity. So there the final velocity is going to be 0. At this point, the v final is going to be 0 in the x direction, v final in the x direction. But in the y direction, there is some velocity because there is no loss of energy here. There is no loss of energy here. So the jet strikes it, and then the jet is just going in this direction, going in the perpendicular direction of the jet of the water. So we will see in more detail. See, the force exerted by the jet on a stationary plate. There can be some cases that on the stationary plane, the plate can be in vertical direction, like the plate can be vertical to the jet. The plate can be inclined to some certain angle to the direction of the jet. The plate can also be curved, and when the plate is curved, there can be three more cases. One case when the jet is striking at the center. Second case when the jet can be striking at one end tangentially and the plate is symmetrical about the x-axis. And the third case, the plate is curved and the jet is striking tangentially at one end when the plate is asymmetrical about the x-axis. So there can be some all different cases, and we will discuss about all the cases, and it's very easy. Once we start understanding this very class, it will be very easy for us to discuss about all of them also. So now let us go on and see. I already told you that at this point the velocity is 0, right? So if I want to draw it like this, just a free body diagram I can say. So this is capital V, right? And what about the Vx, right? I can say the velocity in the x direction. This is going to be 0. Why? Because if I want to find the component of this velocity in the x direction, that is going to be 0. How? Because there is 90-degree angle between them. So the component here is going to be V cos 90, which is basically 0. So there is no component of the velocity capital V in the x direction. Now you can say that this is capital V, which is the initial velocity, and this is the velocity which is coming out. Like I can say the jet after striking the plate will move along the plate. But the plate is at the right angle to the jet, hence the jet after striking will get deflected through 90-degree. Hence the component of the velocity of the jet in the direction of the jet after striking will be 0, which is shown here, right? And we are assuming that this capital V is the same velocity as this velocity, which is moving along the plate. As there is no loss of energy, we are assuming it, okay? After that, you can see that we are considering some things, that the jet of water coming out from the nozzle strikes a flat vertical plate with the velocity capital V, and the diameter of the jet is capital D, and area of the cross section of the jet is pi d square over 4. You can see that this is going to be the diameter. Now we are more interested into finding out the rate of change of momentum in the direction of the force, which is Fx. So first I will show you the calculation. So Fx is basically, I showed you earlier that it is going to be m over dt into dv. So dv basically means initial velocity minus final velocity. So m over dt is basically mass flow rate, and dv is basically initial velocity minus final velocity, right? So mass flow rate can also be written as rho q. So initial velocity in this case in the direction of the jet, in x direction, you can say this v is the initial velocity and the final velocity here vx was 0. We know that, right? So I can say the initial velocity is capital V and the final velocity is 0. And we can also further write this rho q as rho a v into v minus 0. How I am writing this thing here, that mass flow rate is equal to rho q and rho av. These three things I am going to explain here. Mass flow rate, what is the unit of mass flow rate? That is going to be kg per second, right? Mass flow rate is kg per second. And now if I want to write it equal to rho q, rho means the density of the fluid. Here in this case it is jet of water, that is 1000 kg per meter cube. So I can write the unit as kg per meter cube into q. Q is the discharge per second. So discharge per second is meter cube per second. So I can find it as kg per second. See, so I can write kg per second, which is the mass flow rate, or m over dt kg per second is equal to rho q. I can find it by the dimensional analysis. Then I can also find it as rho av, right? So rho q is equal to a into v. Here a is the area of the cross section of the jet and v is the velocity, that is that initial velocity of the jet. So here I can find that rho is basically the density again, so kg per meter cube, and a is the area of the cross section of the jet, which unit is meter square, and v is the velocity, so meter per second. Here you can also see meter square and meter is going to be meter cube, and this meter cube and this meter cube is cancelled. We can find kg per second as the unit. So I can easily write this mass flow rate here. I can write this mass flow rate is equal to rho q and this is equal to rho av, right? And after simplification I can get rho a v square. So this is the force exerted by the jet on the plate, right? And if I want to find the force exerted on the jet by the plate, that is going to be minus rho a v square. Okay, it is according to the Newton's third law, that Fx, if I apply this force, is equal to minus Fx. Okay, in the direction of x. So afterwards I will erase all of them and let us see. I have written that rate of change of momentum, initial momentum minus final momentum by time, mass into initial velocity, final momentum as mass into final velocity over time. I am just taking common mass over time is initial velocity minus final velocity. Then I can find mass over time is rho q into initial minus final velocity. Q is equal to AV. I have already showed you how you can write that. Then you will find the initial velocity as capital V and final velocity is 0 in the direction of x only. I can say it is in the direction of x only, right? If I am finding in x direction. So here at this point the V final at x direction is 0, right? But there is some velocity, the same velocity, which is the initial velocity of the jet of the water. With that same velocity the jet will move along the plate. So this is also capital V. This is very important, and this is also V. It is moving with the same velocity. So rho AV into V minus 0, I can find rho AV square. So this is the force exerted on the plate by the jet. And what about the another case when the plate is applying some force on the jet of the water? For deriving above equation, we have taken initial velocity minus final velocity and not final minus initial. If the force exerted on the jet is to be calculated, then final minus initial velocity will be taken. I have already told you that this is going to be minus rho a v square, which is the force exerted on the jet. Force exerted on the jet is minus rho a v square. And how we can find that? That is found using final velocity minus initial velocity. Yeah, this is the end of this lecture. Thank you so much for listening till the end. If you find this video helpful, please like and subscribe to my channel.